Hello and welcome to the Magnetic Interactions unit of Phys 1204. In this video lecture we're going to look qualitatively at some features of magnetic interactions, and in particular I'm going to focus on how they are different from electric interactions. We'll start off with the very simple observation that there are some objects which will attract iron objects, such as iron filings, paper clips, nails, bolts, and so on. But these same objects will not attract other things, such as paper. The fact that they won't attract paper tells us that this is not an electric interaction, it's something new. This is a magnetic interaction, and we'll call these objects magnets. All magnets have two poles, and in particular if you suspend a magnet so that it's free to rotate, there's one pole that will always end up pointing north. We call that its north-seeking pole, and the other end is called its south-seeking pole. We'll often abbreviate that just to North Pole and South Pole, but it is clearer to call them the north-seeking and south-seeking poles. And note that no matter what shape a magnet is, it always has both poles. For example, a horseshoe magnet is just a bar magnet that has been bent. So far, I probably haven't told you anything that you haven't known since you were quite a small child, and all of this was known to humans in antiquity. Even briefly playing around with two magnets shows you that like magnetic poles repel each other, so two south-seeking poles will repel and two north-seeking poles will repel, whereas unlike poles attract each other. You may notice that in these forces I'm using B to represent magnetic forces. Why B? Why not M? Well, don't worry about it. It's historical. The reason a compass needle works is that it's just a small magnet, and the reason all magnets will turn so that one end seeks north is that the Earth itself is just a big magnet. Note, however, think about what kind of magnetic pole must be at the Earth's North Pole. Since north-seeking poles are attracted to it, it must be a south-seeking pole. That may seem confusing at first, but once you think about it, it makes perfect sense. Note that the magnetic pole of the Earth is not at the geographical pole of the Earth, and in fact the magnetic pole wanders, as this map shows. The north end of a compass will be attracted to any south-seeking pole and repelled from any north-seeking pole. This makes a compass very good for diagnosing which pole is which on a magnet that isn't labeled. So for example, this rare earth magnet is unlabeled. The red end of the compass needle is the north-seeking end, the black end is the south-seeking. So now since we see one face attracts the red end and the other face attracts the black end, then the face on the left must be the south-seeking end, and this one on the right, which attracts the south-seeking end of the compass, must be the north-seeking end of this rare earth magnet. So here I've wrapped a rare earth magnet in paper and labeled its north and south poles, and I've got a stack of rare earth magnets that I've put on rails so that they are held to slide back and forth and not rotate, and you see the north-seeking pole will repel one side, the south-seeking pole will repel the other side, but if I flip it around, attract. There are several common misconceptions about magnets. One of the most serious is that some people think that the north-seeking pole of a magnet attracts iron objects and the south-seeking pole repels. But that's absolutely false. Both poles will attract iron objects, and you can easily see this yourself. Take any magnet, and you can use another magnet to verify that it has both types of poles. In this case, I don't know which pole is which, but I can certainly see that it has both types. And then you can verify that both poles will pick up something like a paperclip. The other big misconception is that magnets attract any metal, but they certainly don't. A magnet won't attract copper or brass. Magnets attract ferromagnetic materials, and the most common ferromagnetic materials are iron, cobalt, and nickel. That's what most magnets used to be made of, but these days the strongest magnets are made out of various exotic high-tech ceramics. Perhaps the most serious misconceptions, though, that people have about magnetic forces is confusing them with electric forces. So I'm going to reiterate what I've already said. Magnetic forces and electric forces are different. Magnetic poles are not charges. Charges are not magnetic poles. Although it's easy to see why there would be confusion because there are some real similarities. Magnetic forces are exerted by poles, and there are two types of poles, north-seeking and south-seeking, and like poles repel and unlike poles attract, just like the way positive and negative charges interact. However, note that both poles of a magnet are attracted to a charged object. That's because that attraction is just the familiar polarization of the magnet, the electric polarization. And so this attraction isn't a magnetic force, it's an electric force. It's occurring because both signs of charge attract neutral objects by polarization, and the magnet is neutral. However, both poles of a magnet attract ferromagnetic materials, and this is because of magnetic polarization. So this is probably another reason for the confusion. This actually looks rather similar. You will have noticed that when you pick up a paperclip, say, with a magnet, that paperclip can then pick up another paperclip. That's because a ferromagnetic object in the vicinity of a magnet becomes magnetically polarized. It has a north pole and a south pole. However, this is a good time to point out another contrast between electric forces and magnetic forces. When you take a charged object away from a neutral object that it's polarized, that neutral object immediately depolarizes. But we often find that when we've magnetically polarized an object, that polarization can last a while. In fact, for example, if you leave a nail stuck to a magnet for a long time, you'll find that it has now become a magnet, and it will remain magnetized for quite a long time. Another big difference between electric forces and magnetic forces is a difference again between charges and poles. Electrically charged objects can be positive or negative or neutral. However, all magnets have both a north-seeking pole and a south-seeking pole. Isolated north poles and south poles have never been observed. In fact, if you take a magnet and you cut it in half, you might think that this would give you an isolated north pole and an isolated south pole, but it doesn't. You get two smaller magnets, each of which has its own north-seeking and south-seeking pole. I'd like to show you cutting a magnet in half. I don't have any cheap disposable magnets, but I've got lots of nails. And if you've got nails and magnets, you can make as many more magnets as you want. So I've magnetized this nail there. You see that's clearly the south-seeking end because it attracts the north-seeking end of the compass. And that end is clearly the north-seeking end. Now I'll cut this nail in half. And now here's half of the nail. And you see that one end attracts the south-seeking end of the compass, and the other end attracts the north-seeking end. So I've cut the nail in half, and half of the nail is a complete magnet with two poles. Let's check your understanding of all that. Let's say we have a bar magnet and we've put it close to a stationary negative charge so that the negative charge is near to the south-seeking pole of the magnet. So which of the choices below is the correct description of the magnetic force that this bar magnet exerts on the negative charge?